Sections 4.4 through 4.6, looking at acceleration and free fall. This is a review of the things we've been doing the past couple of days in class. If you remember, acceleration is defined as change in velocity, I'll use v for velocity there because I've run out of space, over the time interval during which that change takes place. So if we write that as an equation, little a always represents acceleration. Change in v would be delta v, change in velocity divided by the time interval t. And delta v we can define further as the final velocity minus the initial velocity. So v0 is our initial speed, or the velocity at time t equals 0. It's the speed our object was traveling at when the clock started. And v is the final velocity. And so that means I can write the acceleration as final velocity minus initial velocity divided by time. It's not just the change in velocity, but it's the change in velocity divided by the time over which it occurred. And the units of acceleration are the units of speed, or velocity, meters per second, divided by seconds, and so that is equal to meters per second squared. It's a rate of a rate. What that means is an acceleration of, say, 2 meters per second squared, or 2 meters per second means that the speed of an object is changing by 2 meters per second every second. To give one idea of how to think of acceleration, I have a little demonstration here. If we can imagine, if you imagine what I've got right in front of me here, which is a cart on a ramp. The cart will start at the bottom of the ramp, and at the top of the ramp I have a motion sensor that'll detect the position of the ramp. I'm going to give the ramp a push up, the cart a push up the ramp. It's going to roll up the ramp, slow down, stop, turn around, come back down again, and we're going to see the speedometer for that cart as it goes up and down the ramp. So as I run the cart up the ramp, what you should see the velocity do in a minute is suddenly change to a negative value, maybe -1, -1.5 meters per second as I get the cart moving. And then you should see the velocity steadily increase from -1.5, wherever it started, through 0, up to +1.5. The minus velocity, the negative number, indicates that the cart is moving up towards the detector. It's just indicating the direction. So we'll see it have a negative velocity that's decreasing until it reaches 0 velocity at the top of the ramp. And then the velocity increases, moving away from the ramp, so positive, coming back down the ramp. And what I want you to pay particular attention to is the speed with which that big red needle moves as we do this. So I hit the start button. I get my cart in position to start, and I'm going to push it now. I'll do it again in a minute, but you should see the velocity jumps to a large negative value and then moves steadily from negative to positive as it slows down. Okay? And what's happening there is that what I want you to see from that is that the needle moves at a constant rate. It's steadily moving from left to right as the cart slows down going up the ramp, instantaneously stops at the top and turns round and goes back. So whereas the velocity of the cart is the rate at which it covers ground, the acceleration of the cart is basically the speed of that needle, how rapidly the velocity is changing. If I put my cart on a much steeper ramp, which I'm going to do now, I'm lifting the ramp up so that it's much steeper. And then again I'm going to hit start and see what happens then. Try again, it slipped. You see how much faster the needle moves on a steeper ramp. That's because the acceleration is greater. The velocity is changing at a greater rate. Now, when it comes to free fall, when you drop an object, all dropped objects fall at the same rate. If we can neglect air resistance like we talked about in class, then they'll all fall at the same rate, and they'll all have the same acceleration, and that acceleration due to gravity is acceleration due to gravity has the symbol little g, and its value is approximately 10 meters per second squared. This means that every second the speed of a free-falling object is going to change by 10 meters per second. And so this table from the textbook just shows that in action. If we drop a ball from rest, at the instant it's let go, it's not moving, and it can't travel any time in any distance in 0 time. So it hasn't traveled at all at the beginning of its trip. 1 second later, it will have accelerated. Its speed will have changed by 10 meters per second, so it'll be traveling at 10 meters per second. 2 seconds later, 20 meters per second. 3 seconds, 30, 4, 40, and so on. And generally, for any time t, the speed it's traveling is going to be 10 times t. And that 10 is the same thing as g here. So we can write at the bottom here that the acceleration due to gravity is causing a change in velocity. The final velocity will be g times t. That's if it's dropped from rest. If it's dropped with some non-zero initial velocity v0, then we have to add that on to its change in velocity, so it's v0 plus gt. Okay? But that's the instantaneous speed at the end of the time interval. V-inst, instantaneous speed. What about the average speed? During the first second, its speed increases from 0 to 10 meters per second uniformly. And so the average speed for which it's been traveling over that first second is 5 meters per second. Similarly, over 2 seconds, it starts at 0, finishes at 20 meters per second. So the average is 20 plus 0 divided by 2 is 10. 3 seconds is 30. 30 plus 0 divided by 2 is 15. And we start to see a pattern. The average velocity is increasing by 5 each time. 15, 20, 25. And in general, it's a half of the instantaneous velocity at the end, which we can also write as just 1/2 of gt, because the instantaneous speed at the end is g times t. And then finally, to try and figure out what distance the ball has traveled if starting from rest, then we just have to multiply the average velocity by the time taken. Remember that our definition of average speed is it's just distance over time. So we can calculate it average velocity times time. So 5 meters per second for 1 second, 5 meters. Travel at an average of 10 meters per second for 2 seconds. 10 times 2 is 20 meters. 15 times 3 is 45. 20 times 4 is 80. 25 times 5 is 125. But average speed times time, if we look down here, the average speed is 1/2 gt. So if d is the v average times t, then it's going to be 1/2 of g t, all multiplied by t, which simplifies to 1/2 g t squared. And so by thinking through that way, we get to 2 equations that'll tell us everything we ever need to know about a falling object. And those equations are: one for answering the question, how fast is it going at the end of any given time interval? Its instantaneous speed at the end of any time period is just going to be g times t. The other question you might want to ask is, how far has it fallen? And the distance it's fallen is going to have been 1/2 g times t squared. Now these equations both apply to an object dropped from rest with an initial velocity of 0. If that initial velocity v0 is not 0, the equations get a little more complicated. We have to include the initial speed, and then we get that the instantaneous speed at the end is that initial velocity times the time plus or minus gt. Let's try and be clear. If we define up as the positive direction, then the instantaneous speed times time, if it's launched upward, v0 will be positive. If it's launched downward, we would signify that as a negative sign. So you'd have a negative initial velocity. And then we'd have minus 1/2 gt squared. And that's because the acceleration caused by gravity is downwards, would be in the negative x direction. So we're introducing that minus sign to indicate that. And I'm getting the equation messed up here, so I apologize for that. It's just gt. So if you're launched upward at, say, 30 meters per second, your final speed is going to be your initial speed minus 10 meters per second for every second that you fall. The distance is going to be v0 times t minus 1/2 gt squared. So these two are for v0 not equal to 0. And when we worked with those on those concept development sheets today, they're not as important for this course as these two equations up here.